nanohub.org.
Online simulation, and more for nanotechnology.
So, first of all, to introduce myself to everyone in the audience, I'm Arun Mannodi Kanakitori. I'm an assistant professor at Purdue University in the Materials Engineering Department. So I work with Professor Ali Strachan and many others. So, we would like to welcome Aagam Shah today for this, this workshop, which is part of a series of workshops that NanoHub has been organizing, and many people have been taking part in it. So I would like to welcome Aagam Shah from University of Illinois Urbana-Champaign. So Aagam is a graduate student at UIUC in the Material Science and Engineering Department. He works with Professor Sameh Taufik and Professor Elif Ertekin, who's also on the call. He works on Graphene Rescue. He worked on the Graphene Rescue tool, which is a NanoHub tool, which is designed to be a one-stop solution for analysis of graphene synthesis by chemical vapor deposition. Acts as a database for recipes and provides tools for users to quantitatively analyze microscopy images and Raman spectra. So I think this falls into the general area of research, that is graphene synthesis by chemical vapor deposition. So, we'll hear more about all this as part of the tutorial that follows. So I think, Aagam, you can go ahead and get started.
Thank you very much, Arun, for that introduction. So hello, everybody. Good morning, afternoon, or evening, wherever you are. Thank you very much for signing up for this workshop. I'm Aagam Shah. I'm part of the Graphene project that supports platforms for community sharing of data related to the synthesis of graphene by chemical vapor deposition, which is part of the NSF-funded nano manufacturing node. This is the second workshop in a series of 2 workshops where we explore various clustering methods to segment microscopy images. We will be working with microscopy images of graphene today, but these techniques, the ones that I discussed last time and the one that we will discuss today, are going to be applicable to most materials in general. So let's get into it. We'll start by just a brief overview of graphene. For those who attended this last time, these first couple of slides are going to be the same, but for those who are new, graphene is a 2-dimensional material. It's a 2-dimensional sheet of carbon atoms that are arranged in a hexagonal lattice or a honeycomb lattice, and it has many desirable properties like high strength and good electrical conductivity, and some relevant applications like transparent conductors, sensors, and flexible electronics. So it's a novel material and quite fun to work with. These are what microscopy images of graphene look like in general. So we will be working with some of these images and a few others. These darker regions, generally hexagonal in shape, are what the graphene domain looks like. The rest is the substrate or contaminants. Every now and then you have shapes that are not hexagonal, like rectangle over here and some other places. So as you can see, there is quite a bit of variety in the contrast, which really makes our job difficult to try and segment these images, but we're still going to try, so let's see. So next is, what is image segmentation in general? It's a way of separating an image into regions that contain shared attributes. So we should be able to tell a person from a handbag from a car. Basically, that's what image segmentation is. In our case, we will be separating graphene from everything else, which is primarily the. So the goal is that once given an image, we analyze every single pixel and determine whether that particular pixel corresponds to graphene or something else, and we label that as not graphene. Humans can usually recognize that, all right, this is graphene, this is the substrate, and this region here is the contaminant. And we can give a qualitative idea of what is where, but we need quantitative metrics so that we can calculate things such as the percentage of area covered, or the hexagonality of the domains. The reason we need to automate all of this is that to analyze hundreds or thousands of images at one time, a human cannot, if we have some human input, even just one click, making so many clicks after you first see the image, you process it in your head, and then you make that click is going to take a while. So we need to automate this segmentation process of identifying graphene and not graphene to to segment these hundreds or thousands of images. In the previous workshop, we discussed two techniques to segment microscopy images. The first was template matching. The basic idea is we choose a region that corresponds to graphene. So something like this red box here, this region here has graphene. All these regions here, darker regions are graphene, and the regions with the some white dots and everything is the substrate and the contaminants. So the idea is we select this area and we try to find regions that are similar to it. The other technique that we discussed was k-means clustering. Now, in k-means clustering, what we do is we input the image. This is an unsupervised machine learning technique where we input the image, and in the output we get k number of regions. In this case, we have 3 regions: this brownish kind of region, the dark blue, and the light blue region. So the program or the code divides the image into 3 or k number of areas, and then it's our job to label what area corresponds to graphene and what corresponds to not graphene. Now, both these methods are semi-automatic, so we don't need to label every single pixel manually, but they require some amount of human input. In template matching, we need to decide the position of the template, the size of the template, and the threshold or the degree of similarity that we are willing to consider as graphene. In k-means, there are the most important is the number of regions, which is the value of k, and we also need to label which once we get the regions, we also need to label the regions as graphene and not graphene. It doesn't do that for us. A few other parameters are the size of the window and the stride length, which are more inherent to the way the particular process works, and we discussed that in the previous workshop. For those who haven't seen that, who couldn't attend the workshop for some reason, can always look at the recording, which should be up in a few days on the NanoHub website. But yeah, in general, both of these techniques require some amount of human input, and doing that for thousands of images is not possible. So we resort to neural networks, which are essentially automatic. So these are things that do require a lot of input data. So initially, to train the network, there is a lot of human input required. But once that effort is made, once we have a well-trained model, we essentially need no human input and can segment a bunch of images in an automated fashion. So what we do, the general workflow that we plan to use is this. We start with an image or a microscopy image or an SEM image. An SEM image is basically an image that comes out of a scanning electron microscope, which looks something like this, or all the images that we'll be dealing with. We then use techniques like k-means and template to generate this segmented image, which we also call a mask. And we use these masks as training data. So we generate a lot of these, a few hundred of these, and we use them as training data to train a neural network. From this, when we train this neural network, we essentially get a model that which is just, I will explain what it is as we go through the presentation. But yeah, we essentially get a model, and we can use that model to segment, automatically segment it after that. So once we have this nice trained model, so we can use this to segment the remaining images that we have. So say, for example, we have 1,000 images. We use the first 100 to train the model, and then the remaining 900 can be done automatically. So yeah, today's topics will be we will train UNet convolutional neural network, and then we will also learn how to detect graphene using this neural network. What is a neural network? Let's get into the basics and I'll give you a brief overview of what a neural network is and what we'll be working on. In the interest of time, I won't really go into much detail, but just to give you a flavor of what it is. So a neural network is basically a network of artificial neurons. So an artificial neuron is basically an entity that takes a bunch of inputs, performs some function on it, and then gives us an output. This here is what a simple neural network looks like. It has one layer of neurons, that is the input layer, then one hidden layer of neurons, and then one output layer of neurons. A deep neural network is a neural network that has more than one hidden layer. It can be two or more hidden layers in this particular neural network. Now we will be working with convolutional neural networks. So a convolutional neural network is where the function that is performed is essentially a convolution function. We will see what it is in a minute, but the function, at least one of the functions that we perform is a convolution function. So this is what the architecture of a neural network looks like. In general, each arrow that you see here, the blue, the red, the gray, each of these is a different function that we perform. The blue arrow is a convolution function. The red arrow is called a max pooling function, and the green arrow here is called an upconversion or a transpose convolution. I should briefly explain each of these functions shortly. The key takeaway here is that, and you will see this once we go to the Jupyter notebook, is that Python libraries have made it such that we don't really need to understand these complex functions to be able to implement them. We can just, use somebody else's work essentially and make really good neural networks. So what is a convolution function? Basically, it takes an input, which is an array. In our case, we reduce our image to a two-dimensional array, and we perform a matrix multiplication on it. So this matrix right here is called a kernel or a filter. We will see what the importance of this is later to the model, but we take this particular kernel, in this case it's a 3x3 kernel, we apply it to the first 3x3 window here, perform a matrix multiplication and get one value here. Then we move one step over, then we multiply it again and we get the next value here. We go one other step over and we get the next value, and so on and so forth. So this is basically a convolution operation. What you see here is that usually, this is what usually happens, is that the size of the input is usually slightly larger than the size of the output that you get from a convolution function. This is one thing that we need to keep in mind for this particular session. Next is the upconversion or a transpose convolution. This is something like something like a reverse convolution, where the output is slightly larger than the input. What we do here is we add a few dummy values, dummy matrix values or dummy cells to this particular input matrix. So we initially have a 2x2 matrix in this particular animation, where we add a lot of dummy pixels, and then we call these pixels, dummy pixels, padding. So we add some padding and then we perform a convolution function on it to get a resultant matrix or an output, which here is a 5x5 matrix. You can do the same thing with the 3x3. We start with 3x3 and get a 5x5 matrix here. So the kernel and the output need not be exactly the same as the input for the convolution. It's not a reverse convolution, but the size of the output is generally similar to a reverse convolution. The last operation here is a max pooling operation. This one is pretty simple. It's just a way of compressing information and reducing the size of the matrix. So in a 2x2 max pooling operation, what we do is we take a 2x2 window in this matrix, we find the largest value in that window, and we just take that one. Do the same for the next one, and the next one, and we essentially an output matrix that is half the size in both dimensions. So back to the unit, you can see these blue arrows here are convolution operations. Next, we perform a max pooling operation, and then this unit of 2 convolutions and 1 max pooling, we perform that again and again and again. We do that, and we finally get this representation here, which we call the latent space, and then we perform 1 upconversion and 2 convolutions, and then this unit is performed again and again and once more, and then we finally perform 1 last convolution to give us the output. The left half is called the contracting path. Here we contract the image. In this case, you can see it's a 572 cross 572 pixel image. We contract this image to a 32 cross 32 pixel image, but with many more layers. And then we finally expand this back to the size that we want. The right side is called the expansive path. So when we contract the image, we are essentially losing some data. What we do is we retain only the most relevant information. In this latent space here, the 2 images of graphene that look different at the beginning here will look almost the same. When we decode these images, ideally they should give us the same output, but since these are 2 different images, we need 2 different outputs. So we perform these functions which are represented by the gray arrow, which is the copy and crop function. So we crop a small part of this layer here, and we copy it over here, so that we start imparting some spatial awareness to our decoding information and get a much more useful output. In general, convolutional neural networks have proven themselves to be very useful for image processing. It allows us to not have to connect every single pixel to each other from the starting image. We can reduce the image to a much smaller size in this latent space, and then connect only those pixels. I think we can, yeah. So basically, what is training a unit like? These are the initial images that we have. So this is the image, and this is the mask or the segmented image. When we train our model, what we try to do is we try to find the optimal value of the kernels for each one of these. So we have kernels everywhere. Every time we perform a convolution, we have multiple kernels. And what we try to do is we try to find the optimal value of these kernels that will give us our desired output. So how do we do this? We first take our entire data set and we divide it into 2 parts. We divide it into a training part, and we divide it into a testing part. The training part is what we use to find the values of these kernels and generate that model. And the testing part is what we use to test our model or test our kernels on some data. So we want to know how well our model is actually doing. So we use this data to test our model. Next is what is an epoch? Well, an epoch is basically one attempt to improve the kernels so that we get a higher accuracy. What this means is, so when we perform this entire training function over a certain data, we get some accuracy from our model. We test it on the testing data and we get some accuracy. We do this over and over again. Every time we do one of these, it's called an epoch. And as we increase the number of epochs, we increase the accuracy of our model. The loss is basically just a way to calculate the error that we have. So our model is not going to give us an exact answer always. There will be some error. So the loss is just a way of measuring the error that our model gives us. So as you can see here, the more epochs generally means a better result. We have higher accuracy and lower loss. But if you see, this levels off after a certain point. After a certain number of epochs, we don't really have a lot of improvement, and this means that you can stop at this point. I see there's a question which says, does the batch number mean epochs? Yeah, here the batch number means epochs. For the function that we use, the graph is generated just says batch number by default. So I think next the Jupyter notebook and actually train such a network. Please navigate to nanohub.org/tools/image segment on your browser. Make sure you're logged into your NanoHub accounts and click on this launch tool button right here. So let's move to this page. I can also post this link to the chat for everybody's convenience.
So, Aagam, while people open up the notebook, do you mind answering a couple of questions that you see in the chat?
Sure. So this particular code that we will be using today isn't going to be open source, but it will in say about a week. Is that a binary mask? Yes. So we eventually apply a binary filter to it and we get zeros and ones. Yeah, initially what we get is not just a binary mask. So initially we get a range of values, but we apply a binary filter to generate a mask. Yes, the mask means is a binary mask. So we get essentially regions. So it will be defined as region 0, region 1, region 2. And we can just, it's not exactly binary, but we can use that to create a binary mask. Is the unit restricted to the images? I'm not so sure, but sure about it being restricted to the images. So there's a consider the optimal number of epochs. Well, we find an accuracy that that we're okay with, essentially. That's how we select the optimal number of epochs. We wait for the accuracy to go up to a value that's good enough for us, and then we stop. We can also increase the number of images in the training data so that we can get a better accuracy from our model. That is also possible. I think we have questions here. All right, so I hope everybody's clicked on the launch tool button here. That should bring the page that looks something like this. Please click on the link here that says training a unit model for detection of graphene. That should open a Jupyter notebook. For those who are new to Jupyter notebooks, this is basically a neat way to write some Python code. This unit here, this one that's selected here, the blue edge, this one here, each of these are cells. You will see there are two types of cells, one which has text and the other which has code. If you want to follow along with me, you can run each of these cells with the code by clicking the run this cell button here or the button here. You can also press Shift Enter on your keyboard to run each cell. So yeah, let's get into it. We start by importing the relevant libraries. So let's click on that. Next, we will be defining the parameters. So here, for those who want to follow with me, I would suggest you decrease the number of epochs to 1 instead of 5, since it's only a 1-hour workshop and it'll take some time to train. And I would ask you to run every single cell if you're following along with me, so that we have a result by the time I reach the bottom. All right, so let's go back up and run every cell. It's going to run sequentially, so it will take some time. Hopefully it's done by the time we're there. So let's define the parameters. The first parameter that we are defining is the number of epochs. Normally it's going to be a lot more than 1, but here we are doing this in the interest of time. Next is we're going to import our data. So we define the path of our images and the masks. We divide our data into testing and training data. Here we have only 18 images. We will be taking 2 as part of our testing data and 16 as part of our training data. Normally you have a lot many more images, and we'll see how that actually helps us. Next, we'll display the raw SEM images here. So these are the images that we're using. The first 2 are part of the test, and the remaining are part of the training data. Next is the masks. So for each one of these, we have some masks, and we're going to use these to train our model. So let's define the architecture. This cell that is commented out is the full unit architecture. We will be using a much more concise version of this, but this is the actual full architecture. As you can see, there are many layers. So each one of these, each layer you see here, the input, and everywhere you see the quantity, the max pooling. Each one of these is essentially one layer in our neural network, which is a huge neural network. So as you can see, we first define our input size, which is the size of our input image. It's going to be a 256 cross 256 pixel image and only one layer. And next, we define the input layer. So we use the input function from the Keras module. I just let him mention, there we go. So I'd like to mention the Keras library is the main library that helps us do all of this machine learning. It's a very, very powerful library, and for those who are more interested in machine learning, you can always look at some of the documentation to see what functions Keras has to offer. So going back down to our cell, so this is the full unit architecture. So we first define the input layer. The only input it takes is the input size. Next, we define the first convolution layer. Now this takes as input the first input layer. Next, we define the next convolution layer. And this takes as input the output from the first convolution layer. And then we perform the max pooling function, where our pool size is 2 cross 2. So we reduce the size of our image to half in both dimensions. This takes as input the output from this second convolution. Now this thing here, 2 convolution operations and 1 max pooling operation. These operations are 1 unit in the unit, and we take this unit and we repeat it over time. So we define the next convolution layer, which takes the output from the max pooling, then the next layer, which takes the input from the previous layer, then the next max pooling operation, which takes the input again from the previous layer, and so on and so forth. We keep doing this for a while till we reduce the image to a size that we are a latent space which we are comfortable with. What I'd like to point out is in this space, an image of graphene is now essentially divided into multiple parts where each domain of graphene or each grain of graphene. So if you take this image here, each one of these domains is now represented as an independent image. So what is initially 16 images is going to be a lot many more images in the latent space, similar to a lot many more images in the latent space. We perform so many convolution functions on it. Finally, we reach the point where we have to start upconverting. So we perform the first upconversion where we take as input drop 5, which is the output from the previous layer. We then perform the concatenate function. We use the concatenate function to copy and crop the weight cell in the presentation itself. And then we go ahead and perform the convolution layers. Again, we perform one upconversion, then we concatenate, and then we perform two convolutions. We do the same 2 more times. We finally come to a point where we use a 1x1 kernel to perform the final convolution that gives us the output as again a 2-dimensional image or an image with one layer. We go ahead and we define our model. So we say that okay, our model has the input for our model is the inputs, which is particular layer here, and the output is the final convolution, which is content, which is this layer right here. And we have now connected our entire model, every single, so we know what our input is, we know what our output is, we've defined that, and then we've connected our input to the next layer, and then the output from that layer to the next layer, and so on and so forth, and completed the entire neural network. And here is a much smaller version of that. I have quickly removed a few units from the middle, a few such bunches from the middle, so that we save on some of the computational time. But that's really not required if you again have more than 1 hour. Next, we go on and define some of the other parameters for our neural network. I won't really go into and explain the detail of what all of this is, but again, you can always look at the documentation of Keras to see what options we have and what these mean. These are just these are some things that we like to call hyperparameters, which are parameters that we tune to help our model fit our data better. Ideally, we change these and we try different values for these different options for these, but we won't really be going into that today. Final is training our model itself. So we define that okay, for each epoch we start pre-processing the image. Since our initial image is of a different size, we first define the variables that will go into our model. So we call that the out images and the out masks. We create them, and for each of the images in our training path, we use this function called read data. Now, read data is just that we have defined for ourselves in a different file. We're just pulling it from our utility folder. What this function essentially does is it imports the image in that particular file. So it imports the image and the masks. It converts it into an array. Then it will crop the image, resize it to make sure that it's a 256 cross 256 cross 1 image. It means a 256 pixel cross 256 pixels and 1 layer in the 2-dimensional image. Once it does that, we add this image and the mask to our output variables, and then we use the train on batch function to train our model. Again, our model takes as input the images and the masks that we have now pre-processed, which is essentially cropped and resized. And the output that it gives is called the loss, which is something that we've seen in our presentation. All right, while I'm waiting for this to still complete, we can move on to the next cell, and once we get the result, we'll come back to this. So next we test the model on our testing data. So we define our test loss as just an empty list. We pre-process our testing data in the same way since we have to use the same model. So we're going to pre-process our data, use the same function, so use the same read data function, generate the same variables, but now for our testing data. And then we use the predict on batch function to generate a prediction for our testing images. Here we just need to feed it our images or the testing images, not the masks, since we want to actually generate a prediction. We can then use this prediction to generate a bunch of metrics to evaluate our model. So we won't be doing all of that today, but this is just for your information. We can also use this function called the test on batch function, which essentially does all of the testing and outputs some of the common parameters like loss and accuracy. So we use that function, we give it the input of our images and the masks from the testing data set, and we calculate the loss and the accuracy and we output that. All right, so this hasn't trained yet. All right, what we can do is move towards the second notebook for now and wait for the results. Essentially, the result is going to be just a definition of the epoch number, the training loss, the training accuracy, and also the testing loss and the testing accuracy. Finally, here we save the model. This save model unit is just a function that we've created. All it does is saves our model and writes the number of epochs and the value of the accuracy. So the testing loss one is basically just the value of the testing accuracy. So while we save our file, we know what the accuracy of our model is, and in case we get a better model, we can use that file for our future requirements. So yeah, let's wait for this to train. Meanwhile, could you please get back to the landing page? For those who have closed this notebook or for some reason can reopen nano.org/tools/image segment and click on the launch tool button. That should bring you back to this landing page. Here you can click this link here now, which is the detection of graphene. Now we're actually going to use a pre-trained model to segment a microscopy image of graphene. So again, let's begin. I think we can start by importing the relevant libraries. Again, I'd like to mention the keras.models library, which has a load model function that essentially allows us to import our model and use it to generate, create a prediction. This particular function right here is just to remove all the warnings that we get from TensorFlow or keras. So let's run the cell. Next, we define the path of the model, the file that we have. So here you can see we trained it on 99 epochs with an accuracy of 0.974 or 97.4%. The This is a model that we trained earlier. We used 58 images and some data augmentation. So we generated some images of our own from those 58 images and then trained the model on that. We are also going to define the path of the image that we want to use. This is an image that has not been used to train our model. So let's define that. This might take a while to run since we also have training running. Yeah, let's run this. Next, we import our model. So we use the model function and we load the model. We import our image and we just display the image so that we can see. While we're waiting, I think I will look at the questions quickly. All right, so no, we don't make any changes to the neural network architecture to process the binary images per se, since the input contains of two images, the raw SEM image, binary mask. The So one image is not binary; it's grayscale, and the other one is binary. So we don't really do we don't really make any changes to the neural network per se. All right, so this is what our SEM images looks like. So let's get back to the Jupyter notebook. This is what the initial image looks like. You can see these darker regions here are all graphene. They have multiple contrasts. And the lighter regions in the background are the substrate or the contaminants. Next, we pre-process the image. So we take the image, we just make sure that we record the initial size since we have to post-process the result and bring it back to the initial size. We resize our image, we change the encoding, and we add the necessary dimensions to make sure that the dimensions of the input image is the same as what we used for to train our model. So we run the cell. Next, we run the model, or we actually predict and create. The function is .predict. The function is predict. We give it the input of our image, and it outputs an array, which is essentially a binary mask for our image. It's going to output zeros and ones in a 256 cluster 56 image. We take, so 0 in that image represents graphene, 1 represents not graphene. To find the mean, if we find the mean of that, we will essentially get the percentage of, or the percentage area that contains the not graphene region. So 1 minus that is going to be the percentage that contains graphene. And we then change the encoding of the prediction matrix, the pred matrix. We print the coverage also. So let's see that. And next, we then take this prediction matrix that has a prediction array that has the changed encoding. We remove the additional layers or the additional dimensions. We resize the image to the original size and we create an image object from it. We finally plot our prediction image with the initial input image and see what they look like. So let's give that a couple of minutes. So normally this training right here takes about 8 minutes for me. What I see here, and this happens quite often, is that when a lot of users are on NanoHub using the same tool, it takes quite a bit longer. So last workshop we had this fitting that normally took 1 minute, and it took 3 minutes in the workshop as such. But yeah, there are no images or any output here per se. All we see here in the training notebook is the loss and the accuracy. These values for the loss is generally quite high, around 0.7. For the accuracy is quite low in the training. Sorry, in training it's quite high. So in training our accuracy is also around 0.8 or so. But when you see the testing, oh here, all right. So this time the loss is quite high. It's 0.8. The accuracy is quite low, so it's 0.25. And for our testing, you will soon see the accuracy is even lower. It's around like 0.05, and the loss is also high, which means our model isn't very good as such. But that's just because we've trained it only for one epoch and on very, very, very few images. So detection book. So yeah, the coverage here is 62.68%. And as you can see, the output images, you can see for the most part, our model has done pretty good. Now, just to reiterate, this model that we used here for the detection notebook is a pre-trained model that we trained on 58 images for 99 epochs. So you can see here, for the most part, it's done a pretty good job. It's identified most of the graphene domains well. The borders are quite crisp and they match what we see in the input image. But every now and then you will see it's missed a few domains. So if you look at these two circular kind of domains here, these three domains rather, they're missing here. There are a few blobs, the corners that it's missing, also this region here. So again, this model isn't the best. We can do a lot better. We are doing so while and we're training it on a lot many more images, but for now this is the model that we have. So yeah, this was pretty much all I had to show you in the Jupyter notebook. Let's go back to our presentation. So this is what the unit performance is. This slide is basically just to show you how well the model does on the full data set. So this is the result from our model that we trained. The overall accuracy is 92% and the precision is 88%. Now, accuracy, the difference between accuracy and precision. Accuracy is basically the fraction of predictions that our model got right. So if there's graphene, did it predict graphene, and if it's not graphene, did it predict not graphene? Did it actually segment the image well? While precision is whatever regions it identified as graphene. Is that really graphene? So what proportion of positive identification was actually correct? So if you look at these images here, what that means again from our perspective is that if an image has high accuracy, it means that whatever domain was identified as graphene, was that domain well identified? Was every pixel identified as graphene, or did it leave out some pixels? And what high precision means is that did it actually identify all the domains of graphene right? Or did it actually did it have low precision and identify some domains which are not graphene as graphene, and some domains which are supposed to be graphene, it left them out. So if we see here, the true mask is what we generated using template matching or k-means manually. We made sure that our masks are correct. This is the SEM image here, and this is the mask generated by the UNet model. Here you can see it's a high accuracy and high precision, which means it's a pretty good image. It's identified all the domains of graphene well, and each domain is quite precise. We can see every single is quite accurate. Rather, we can see every single pixel is well identified. The next one is high accuracy and low precision. This means is that it leaves out a few domains that are graphene, and it identifies some regions from the substrate to be graphene. So if you see here, there are quite a few regions that are actually substrate, but the model has identified it as graphene. However, for most of the regions that it has identified, it has done a pretty good job. So every region that has been identified as graphene is quite crisp. It matches what we expect. On the other hand, in the image here, you will see it has identified almost all the domains. So in every domain, you will see there are a few pixels that have been identified to be graphene, but it's left out quite a few parts of those images. This is what it means to have low accuracy. The last one is where we see some images have low accuracy and low precision. So this shows that our model is still a work in progress. We still can do a much better job, and we are doing so. But in general, a UNet is an architecture that allows us to generate a good model with relatively few images, and also use data augmentation. We can use augmented images that we generated to train our model, which is quite handy and unique when we have quite handy when we have a very small number of images at hand. The final slide that I'd like to show you is just this thing that we call a deep net analysis. So in general, neural networks are a black box, but a deep lift analysis helps us to identify which pixels are very, very important in data mining, whether a particular region is considered as graphene or not graphene. So it gives us some insight into what is going on inside the neural network. So from this original image, you can see that the pixels that are darker red have a higher importance in data mining, whether that region is graphene or not. Same way here, the pixels that are darker blue have higher importance in data mining, whether a particular region corresponds to the substrate or not. As you can see here, these pixels are generally concentrated around the edges, and then there are a few pixels in the middle of those domains that are very, very important. And if you think about it, this is the way humans usually do it. We look at the edges to see whether it's really hexagonal to a certain extent, and then we look in the middle to see whether, okay, that region has the same contrast, and okay, we say, yeah, this image is graphene. Same way we say everything else looks like the substrate. It's generally a very uniform region, but we make sure the edges are, we know that the edges are important. And we also look at some of the artifacts to see whether that is graphene or that is contaminant, or that is the substrate. So every now and then you will see some artifacts, the pixels around those artifacts have some higher importance. This was basically, this is a very cool thing, I feel, where the neural network is essentially doing or detecting graphene the way humans do it. I go through a summary. So in the first workshop, we went through template matching. The idea is we identify a region that looks like graphene, and then we try to find regions that are somewhat similar to it and generate a mask. In k-means clustering, we input the image, get a k number of different regions, and then we label each one of those regions as graphene or not graphene. And finally, we have the UNet, where we take a bunch of input images and input masks. We train our model, we test it, we make sure it's quite accurate, and then we finally can use it to automatically predict graphene and not graphene. Thank you everyone for signing up and attending the entire workshop.